Hello, welcome back to MathandBolt. So today we start our lecture with a new topic, central forces. So let us begin by first understanding what central forces are. Suppose, let's say we have a particle of mass m, and this particle is within some force field. Some kind of force field is there. Then in order to categorize this particular force that's acting on that mass m, what we do is we look for a fixed point in space. Let's call this fixed point O. Now what does mean? Usually this is the center of some coordinate system. So that means if we have a familiar XYZ coordinate system, then O is going to be the fixed point or the center of this coordinate system. Then what we do, then immediately we see the force that acts on this particular object of mass m. What we do, we join the fixed point and the position of the particle with a straight line, and then we see along this straight line if the force is either acting towards this fixed point or is it acting away from this fixed point. So this is going to be criteria number 1. So let me write it down. On the force on the particle, some force, we do not know its central force here, we are trying to figure that out. Force on the particle is always directed from m toward or away from the fixed point O. Right. Then we look for the second criteria. The second criteria is that the magnitude of the force must be a function of the distance between the fixed point and the point where the object in study is present. So this will be criterion number 2. The magnitude of the force that acts on the particle of mass m depends only on the distance. Depends only on the distance or measured from the fixed point O. So when these two criteria are fulfilled, then the force that we obtained, the force on this particle that's obtained, is referred to as a central force or sometimes central force field, and the O, the center fixed point O, will be the center of force. So symbolically, if we have the force denoted by F vector, then our F vector must be a function of the distance R, and it's going to be directed along the line joining the fixed point O and the position of the particle. So this force F vector it could be attractive or repulsive in nature. So it is going to be attractive if F of R is less than 0, and repulsive when F as a function of R is greater than 0. So this is what central forces are. Now immediately, once we categorize a particular force as a central force, then what happens? We can talk about the following properties. So let's talk about the important properties. Property number 1 will be, under the influence of a central force, the path or the trajectory of a particle is going to be planar. The path is planar. That usually means that the trajectory of the particle must occur on a planar surface. That is, its movement is strictly restricted to the XY plane only. This is property number 1. Property number 2 says that the angular momentum is conserved. The angular momentum of the particle is conserved. That is to say that L vector is a constant. Now we know that the angular momentum is a vector quantity, and when we say that L vector is a constant, that means including its magnitude, the direction of angular momentum is also going to stay constant. And property number 3, so that will be referred to as the laws of areas. So that means the fixed distance that we talked about between the center or the fixed point O and the position where the particle is. This radius, also referred to as the radius vector, which is the line joining O and P. So this is always going to sweep out equal areas in the equal line. So in a way we can say that the rate of change of area, that is going to be constant. So we will prove each of these properties one by one. So let's begin with the first one. The path is planar. Now the moment we consider the path is planar, then what we will be restricted to a two-dimensional motion, because in a plane we only need two dimensions, either the x coordinate or the y coordinate, to represent the coordinate or the position of a particle in space. Right. So that means if we're talking about the Cartesian system, we'll be sticking to x and y, and we'll be also considering a new coordinate system. So that will be the polar coordinate system, where we need the parameters r and theta. We'll talk about that in details in a moment from now. Now before that, let's talk about the equation of motions that we will be deriving the moment we consider that the path is planar. So whenever we have a planar motion, then planar motion in the sense that we are considering the xy plane to be Cartesian, and the coordinates of this particular point will be in r and theta, that is in the polar coordinate system. Then immediately the equation of motions will be given by mass times r double dot minus r theta dot squared. So that is equals to force as a function of r and m times r theta dot plus 2 r dot theta dot equals to 0, where r dot single dot represents derivative of r with respect to time t. R double dot will be second derivative of r with respect to time t, and similarly theta dot will represent derivative of theta with respect to time t. So our task will be to derive this particular equation of motion, and for that we will need to be familiar with the plane polar coordinate system. Let me write it down. The plane polar coordinate system. So let's try to understand plane polar coordinate system. We begin our discussion with the rectangular coordinate system. So let's consider a two-dimensional coordinate system. So how to identify a two-dimensional coordinate system is going to consist of two mutually perpendicular axes, coordinate axes. So here we have the axis. Let me write it down. The OX, which is also the x-axis, and we have OY, and that is going to be our y-axis. And both of these axes are mutually perpendicular to each other, that is, they're making an angle of 90 degrees at the point of origin O. Now if we have a point P which has the coordinates x comma y, then that can be determined, the position of this particular point can be determined by dropping two perpendiculars, one perpendicular on the x-axis, so that will be BA. So BA is perpendicular on the x-axis, and another perpendicular BB on the y-axis. And the length or the length of this perpendiculars is going to give us the x coordinate and the y coordinate respectively. So that means the value of OA is going to be equals to x. The value of OB will be equals to y. Now, if we consider the right angle triangle OAP, so we can use the Pythagoras theorem. So that will be OP squared. So that's the length of the longest side of the hypotenuse. That will be equals to, we have the base, which is OA squared, plus added to the opposite or the perpendicular. So that's P, let's take it as AP squared. Now OA, so OA is our x squared, and AP, so AP, now this is a rectangle, so the side AP is exactly equals to side OB, so this will be also equals to AP. So instead of AP we have OB, which will be y squared. So this is the length of OP squared. So if we take the square root on both sides, so that gives us the length OP as square root of x squared plus y squared. Now rectangular coordinate system, are very useful only when we're describing the motion of a particle along a straight line. However, there will be certain cases where the particle will not be moving along a straight line, but instead it could be moving in a curved line. In that case, it's very important that we choose a proper coordinate system for making the problem much easier. That means for determining its position in space and other parameters like the velocity and acceleration, which we'll be calculating later on. That becomes easier only when we choose a proper coordinate system. So the next coordinate system that we'll introduce is the plane polar coordinate system. So that coordinate system becomes useful whenever we're trying to find out the motion of a particle that's not in a straight line but in a curved path. So let's do that. So here we have the point P in space. In the rectangular coordinate system, it had the coordinates x, y. Now we will be using two new parameters, which will be the radius r and the angle theta. So that will be the r theta in the plane polar coordinate system. Let's try to understand how we can determine the point's position in space. So all we need to do is from the fixed point O, or the center of the reference frame, we draw a straight line whose distance is measured as r. And this line OP makes an angle theta. So here you can see that theta is going in the anti-clockwise fashion. So that means it's making an angle in the positive direction of x-axis. So just by using the parameters r and theta, we can determine the position of the point P in space using the plane polar coordinate system. Now we want to find out the relationship between the coordinates x and y and r and theta. So let's do that. So if we take a look at the, let's call this triangle, let's say this is P, where PB is perpendicular to the x-axis. So in right triangle OBP, so this is right angle at angle B. Write it down. So angle B is equals to 90 degrees. So in that case, if we apply some basic trigonometry, then our OB, which is actually x, so that will be equals to OP times cosine theta, and our OP is the radius r, so we have r times cosine of theta. So this is how we can express x in terms of r and theta. Similarly, if we consider BP, then BP, which is actually y, and that will be equals to OP times sine theta. So y will be equals to r sine theta. So that means if we know the values of the radius r and theta, then we can immediately go back to the rectangular coordinate system. That means finding the values of x and y. Right, so that means x comma y is equivalent to r cos theta comma r sine theta. We can also go the other way around. So if we take x and square it, so we should get x squared is equals to r squared cosine squared theta. And we have y equals to r sine theta, so let's square both sides. So that will give us r squared sine squared theta. Now if we add both of them, then we should get x squared plus y squared equals to r squared times, so we'll have an identity cosine squared theta plus sine squared theta, so that identity is equals to 1. So we get x squared plus y squared equals to r squared. Rewriting this equation in terms of r, we have square root of x squared plus y squared, and this represents the distance OP, which also in the previous rectangular coordinate system we used the Pythagoras theorem to obtain the same value. So in that case OP represented the hypotenuse, whereas in this case the radial distance r represents the hypotenuse. Then what we can do, if we take the y coordinate or the y component and divide it with the x component, and whatever ratio we get, we take the inverse tangent of that ratio, then this will give us the angle theta. So in other ways we can say that if we have the values of x and y, then we can immediately find the values of r and theta. So that means r and theta equals to, in place of r we have square root of x squared plus y squared, and theta will be simply tangent inverse or the arc tangent of y over x. Thus, in a two-dimensional coordinate system, when you consider the point P represented in either xy coordinate system or r theta coordinate system, they are both going to specify the position of that point in space. Now here, r can have any values between 0 to infinity, because the radius could be as small as 0 and it can extend up to infinity. And our angle theta, so let's say it starts from 0, then it can extend up to 2 pi, which will be one complete full rotation. And this theta is always increasing in the counterclockwise fashion. So we also have unit vectors. So what are unit vectors? They are simply vectors with magnitude of 1 and some particular direction. So we're going to define two unit vectors, I cap and j cap, in a rectangular coordinate system. So I cap simply represents the vector. It's a unit vector that starts from the origin and points towards the x-axis. And we have j cap, which is another unit vector that starts from the origin and it's going to point along the y-axis or in the y direction. So essentially I cap and j caps are unit vectors that points along the coordinate axis x and y. So let's now consider OP. So OP, this OP has got an x component and it's also comprised of the y component. But we cannot write this as simply x comma y because this will specify the coordinates of the point P. What we want to understand is what is the value of this radial length OP. So this is not the right way to write the radial length of OP. So what we'll do, we'll take the x component and multiply it to the unit vector I cap, which tells us like how much of x exists along the x direction, plus the y component. We'll take the y component, which is the y coordinate of point P, and multiply to j cap, and this is going to tell us like how much of y is present along the j direction or the y direction. Right. So that means this is simply x, since the x component is also like the x coordinate of point P, so we have x times I cap plus y times j cap. Now I cap and j cap, these are dimensionless quantity, they only specify the direction, so multiplying x with I cap is also not going to get affected. That means the magnitude of x I cap, let me write it down, the magnitude of x I cap will be exactly equals to the magnitude of x, because I cap has a magnitude of 1. Similarly goes for yj cap. Likewise, we will also have unit vectors in polar coordinates or the plane polar coordinates, and that will be r cap and theta cap. So let's try to understand those as well. So the figure shows an xy coordinate system. So we have an xy plane and those concentric circles are circles of fixed radius. So that means it's a radius of the first circle will be fixed at, let's say, r1, and then the second circle will be fixed at r2. So these are all constant radius circles. Now to understand unit vectors in the plane polar coordinate system, we will introduce two of them. So one is our r cap and other is the theta cap. So let's consider a point. Let's say we're going to 1, 2, 3, 4. Let's consider the fourth circle, and we want to specify the coordinate of this particular point on the xy plane. What we do, the only first thing that we need to do is set the origin at O and then join the origin and that point in question. So this is going to be at a fixed distance. So since this is our fourth circle, so let's call it R4. So this is our R4, or which is the radial distance between the point O and point P. Then we are going to have two vectors. One will be r cap and the other is theta cap. So r cap is going to be the vector which is going to be pointing in the direction of increasing radial distance. So this is our r cap. The unit vector r cap is pointing in the increasing direction of the radial distance, or simply put, as we move along OP, the radius increases. Then we have another, which one is the theta cap. So theta cap will be tangential to this circle at that particular point P. So this is going to be theta cap, and r cap and theta cap forms a orthogonal system, which means they are always going to be at 90 degrees to each other. That means no matter where we look at any point on this circular path, let's consider this particular position and space. So we'll first join them with a straight line. Then this is going to be the direction of r cap, assuming that the particle moves anti-clockwise fashion. Then this is going to be a theta cap. So here also we see that they are mutually orthogonal to each other, just like in the case of rectangular coordinate system. So if we have OP, then what we do is, like, we consider the coordinate of the point P. So let's be r comma theta in the plane polar coordinate system. Then OP will be r times r cap plus theta times theta cap. So the next section will be to figure out what is the relationship between the unit vectors I cap, j cap in the xy coordinate system, and if we transform it, then how does it transforms to r and theta cap, and again vice versa. So when we consider a particle at point P, and if we are using the rectangular coordinate system, then we have the unit vectors I cap and j cap, which are mutually perpendicular to each other, and I cap and j cap helps us find out the position of point P. Now if we decided somewhere that no, this is a very complicated problem and it's much easier to work in the r and theta coordinate system, that is the plane polar coordinate system, then we introduce r cap and theta cap. Now as we can see here, the unit vectors I cap and j cap has rotated by some angle theta to go to r cap and theta cap. That's simply saying by how much amount of theta I cap and j cap has to rotate, so that we end up in a new coordinate frame, namely the plane polar coordinate system. As we are dealing with vectors, so this transformation from I cap j cap to r cap theta cap is going to involve a few steps. So let's try that out. So this particular point is point P. Now let's start with that. So first we begin by considering the x-axis, which has the unit vector I cap, and the y-axis, which has the unit vector j cap, and also the vector r cap, which makes an angle of theta with I cap. Now we want to resolve this particular r vector along I cap and j cap. So for that we have a perpendicular drawn on the I cap. So that means I cap will be equals to r cap cosine theta, and j cap will be equals to r cap sine theta. So this particular height is a r cap sine theta. Next we consider j cap and negative I cap, and we are going to consider the vector theta cap, which makes an angle of theta with j cap. Then we ask the question, like, how much of theta cap is present along negative I cap. So that means negative I cap will be equals to theta cap. So here we have sine theta, and how much of theta cap is present along j cap direction. So that will be j cap is simply equals to theta cap times cosine theta. So let's combine it. So that should give us, along I cap we have r cap cosine theta, r cap cosine theta, and we also have negative I cap. So that means I cap will be simply negative theta cap times sine theta. And along j cap we have r cap sine theta plus theta cap cosine theta. So this transformation takes us from r cap theta cap to I cap j cap. So that means we have to know the value of theta, and if we know r cap and theta cap, then we'll get the corresponding unit vectors in the rectangular coordinate system. Now if we want to go the other way around, that is we want to go from I cap j cap to r cap theta cap. So here what we will do is, so let's consider this equation, I cap equals to r cap cos theta minus theta cap times sine theta, both of these two equations, and we can write it in the form of a matrix equation. So we have a column matrix that comprises of I cap and j cap, that's equals to, we have the coefficients of r cap and theta cap, so that will be cosine theta minus sine theta. So those will be elements in the first row, and in the second row we have sine theta, cosine theta, all multiplied to r cap theta cap. So this is known as the transformation matrix. So that means this particular matrix, this 2 by 2 matrix, when multiplied to the column matrix that comprises of r cap and theta cap, we get I cap j cap. This is how we transform. Using this transformation matrix, we can go from r theta cap to I cap j cap. Now we want to go the other way around. So for that, what we'll do, we'll have to take the inverse of this transformational matrix. So that means we have r cap theta cap, that will be equals to, so let's rewrite the matrix, the transformation matrix, cosine theta minus sine theta. In the second row we have sine theta, cosine theta, we take the inverse of it and then multiply it to I cap j cap. So inverse of this matrix is simply cosine theta plus sine theta. In the second row we have negative sine theta cosine theta times the column matrix I cap j cap, and this is equals to r cap theta cap. So using this matrix equation, so if we have I cap and j cap, and we know by how much angle it has moved, then we multiply this column matrix to this transformation matrix, and that will take us to the unit vector r cap theta cap. Now graphically, if we want to understand how this has happened, so let's again go back to a vector diagram. So we have this point P. Then what we will do is, this time we are going to consider the orthogonal vectors r cap and theta cap. So we consider this particular vector r cap and this vector theta cap, and then we consider the vector between them, which is j cap, that makes an angle of theta with theta cap. And we'll be asking the questions, how much of j cap is present along theta cap and how much of j cap is present along r cap. So that's what we want to find out first. So that will be simply, so let's start with r cap. So how much of j cap is present along r cap? So that's j cap times sine theta, and we have how much of j cap present along theta cap. So that will be theta cap is equals to j cap dot j cap multiplied to cosine theta. Now we will consider another orthogonal system. So for this we take the negative theta cap, just draw in the exactly opposite direction of theta. So this is a negative theta cap. Now we consider the set of mutually perpendicular vectors r cap and negative theta cap, and we will also consider the vector I cap that needs to be resolved. So this vector I cap is making an angle theta with r cap. And then we ask the question, how much of I cap is present along this particular r cap and how much of I cap is present along negative theta cap. So that means we have, for this system, r cap will be equals to I cap times, so here we have an angle theta, so that means made with r cap, so that will be cosine theta. That is how we have how we resolve vectors into its individual components. And negative theta cap, we are asking the question, how much of I cap is present along negative theta cap. So that's equals to I cap times sine theta, or simply theta cap is equals to negative I cap sine theta. So let's write the combined form. So r cap will be, so this part and this part, so we have I cap cosine theta plus j cap sine theta, and for theta cap we have negative I cap sine theta. So this is this particular value added to j cap cosine theta. And if we write it in the matrix form, then we get, let's write it down here, we have the column matrix r cap theta cap. So that is equals to the transformation matrix. So first row will have cosine theta and sine theta, and in the second row we have negative sine theta and cosine theta. So that's multiplied to I cap and j cap, and that's exactly what we got when we use the inverse matrix or the matrix equation. So let's compare both of them. Yep, cosine theta sine theta, negative sine theta cos theta. So yeah, so that means when we have I cap and j cap, and if we multiply it to this transformation matrix, so that is going to take us to r cap and theta cap. Now you might be wondering, how did I quickly write that r cap is equals to j cap sine theta and theta cap is equals to j cap cosine theta? So let's talk about this quickly. This is vector resolution. So what you do is, like, let's say you have two vectors mutually perpendicular to each other. Let's call one as the OA vector and the other is OB vector, and we have another vector which makes an angle theta with OA. Let's call it OC. So OC is making an angle theta with the OA vector. Our purpose is to find out how much of OC is present along OA and how much of OC is present along OB. In other words, we are trying to find out the projection of OC along OA and OB. The trick will be to draw perpendiculars, and OA, that will be simply equals to, so this is OC. Now we look for the angle. Now here it's mentioned here that there is an angle theta here. So since the angle here is mentioned as theta, so this will be simply multiplied to cosine theta. Nothing is mentioned here, so there is no angle mentioned here, which actually is 90 minus theta, but this is a trick that you can use it later on, and I'll show you a few more examples how this becomes useful. So here you check out that there is no angle mentioned here, so we have OB, so that will be simply equals to the vector that we want to resolve, the OC vector, times sine theta. Now this is a very simple problem which helps us quickly get the value. So like in the example that we just did, in the illustration that we worked with for finding out I cap, j cap, or r cap and theta cap, that was that looked a little bit complicated in the sense that there was an orientation, it was making some angle theta. So I'm going to show you the same trick, but this time we're going to orient this mutually perpendicular system by some angle theta with respect to the horizon. So what I mean to say is, like, let's say suppose we have this time OA vector oriented in this particular direction, and this is our OB vector, and we take OC vector, but let's say this time OC vector is making an angle phi with the OB vector. Then the question is to ask out how much of OC is projected along OA and OB. So what we do, we quickly draw perpendiculars. This is just for our aid. So this will be like the projection of OC along OB, this particular portion. So we just call it OB. So that will be OC multiplied to, now we see that there is an angle which is specified as angle phi. So we'll simply multiply it to cosine phi. While for the other one, which is OA, there is no angle mentioned here, nothing is mentioned here. So we'll simply write it as OA will be equals to the vector OC. Always consider the vector that needs to be resolved, OC times, since no angle is mentioned, that will be simply sine of the angle phi. Now if we go back to our original problem, this is what I did. So in this case, so when we are finding out r cap and theta cap, we considered, which one? We considered this two mutually perpendicular axis. One is your r cap axis and our other one is the theta cap axis, and we wanted to find out how much j cap is getting revolved or projected along r cap and theta cap. So j cap is making an angle theta with theta cap, so that means how much of j cap is along theta. So that is simply given by theta cap is equals to j cap, the one that we were resolving, multiplied by some angle, right, which is theta. And since theta is mentioned here, we used cosine theta, and on the other side there was no angle mentioned, so we multiplied with sine theta. So you can pause the video and check out in both the two cases. And this is how we have obtained the relationship between I cap j cap and r cap theta cap. So now that we have obtained the transformation to go from I cap j cap to r cap theta cap, or the other way around, let's use the transformation of I cap and j cap going to r cap and theta cap. So that means from the rectangular coordinate system to the plane polar coordinate system. So we obtained the equation r cap is equals to I cap cosine theta plus j cap sine theta. And for theta cap, we obtained negative I cap sine theta plus j cap cosine theta. So clearly we see here that r cap, the unit vector along the radial direction, is purely a function of theta, and so is the theta cap unit vector. This is also a function of theta alone. Now that means what we will do, well, let's take the derivative of r cap with respect to theta. So that should give us, so we have I cap times derivative of cosine theta is negative sine theta, plus j cap times derivative of sine theta will be cosine theta, and this is simply theta cap. Next we take the derivative of the unit vector theta cap with respect to theta, since it's a function of theta, and that should give us negative I cap times derivative of sine theta will be cosine theta minus j cap sine theta. And if we take the negative common, so that will give us negative r cap. So this is what we have obtained, but let's try to understand it visually. What's actually the meaning of d r cap over d theta and d theta cap over d theta. Let's consider the unit vector r cap at the angle theta. Let's say that the angle theta increases by d theta amount. So that means the radial unit vector is going to change from r cap theta to a new position. So let's call it r cap theta plus d theta. Next, we need to ask by how much amount r cap theta changed when theta incremented by d theta amount. And that is simply given by the displacement dr cap. This is equivalent to saying by how much amount r cap has changed for every theta increment from theta to theta plus d theta. This is exactly equals to a vector. So we have obtained a unit vector, and this unit vector is exactly the same direction as theta cap. So that means this is equals to theta cap, right? And we also got the same result when we second the differentiation of r cap with respect to theta. Next, what we will do is we are going to increment theta. So we said that initially theta cap is a function of theta, and we let theta cap, and that means theta cap increase in the sense that we are again increasing theta by d theta amount, such that our theta cap is now at the position theta plus d theta. So that means there has been some displacement that has taken place. Let's use a different color for this. So this much displacement has taken. So this displacement is along the theta cap direction. So this is d theta cap. So d theta cap has happened per d theta change. So that is equals to some vector whose direction is exactly opposite to that of r cap. So that means in the negative direction of r cap. And this is the result that we obtained when we took the derivative of theta cap with respect to theta. So for the point P, the position vector is given by r vector, which is simply equals to the magnitude of r vector is r times the unit vector, which is along r, the radial direction, and that is a r cap, which is a function of theta. Now what we will do, we'll try to find out the velocity. So the velocity will be simply v vector is equals to the rate of change of r vector. So that is equals to the rate of change of, so r vector is simply r times r cap of theta. So we use the product rule, so that will be dr over dt times r cap plus r times d r cap over dt. Now dr over dt, so that's simply the time derivative of distance r, so that will be replaced with r dot r cap. So let's write it down, where r dot is simply dr over dt plus r times, so we have dr cap over dt. This can be also written as dr cap over d theta times d theta over dt. So here we have used the chain rule, and this is done specifically so that in place of dr cap over d theta, we can replace this with theta cap. So that means we will get r dot r cap plus r theta cap times theta dot, where theta dot is equals to theta dot is equals to d theta over dt. That means derivative of theta with respect to time t, and this is the expression for velocity v. So here we immediately see that our velocity vector has two components. One will be the radial component of vector v, and this is simply v of r, which is given by r dot, or simply dr over dt, and its direction is along r cap. That's why it's called the radial component. So it has to be along the unit vector r. Then we have the angular component. The angular component of velocity v vector will be v of theta, which is equals to this second part, which is r times theta dot, and this will be directed along theta cap. So we have the radial as well as the angular component. So again, now we'll differentiate the velocity vector with respect to time theta, and that will help us obtain the acceleration. So acceleration will be given by rate of change of the velocity vector v, and velocity vector v is equals to, so let's use the value. So we have r dot r cap plus r theta dot times theta cap. So we're going to take the derivative of each terms with respect to time t to obtain the acceleration. So let's do that. So this will be equals to derivative of r dot r cap, so that will be ddt of r dot times r cap plus r dot dr cap over dt plus ddt of r theta dot all multiplied to theta cap plus r theta dot multiplied to ddt of theta cap. So ddt of r dot will be r double dot. That simply means that we have taken a double derivative. So r double dot is simply equals to ddt of r dot, or this is equals to d square r over dt square. Essentially all of them means the same thing, times r cap plus r dot. So we have dr cap over dt, so that can be written as dr cap over d theta times d theta over dt. So we've again applied the chain rule, plus we have ddt of r theta dot. Let's apply the product rule. So this will be dr over dt times theta dot plus r times d theta dot over dt whole multiplied to theta cap plus r theta dot. So we have d theta cap over dt, so that will be d theta cap over d theta times d theta over dt. Here again we have also applied the chain rule. So this will be r double dot r cap plus r dot. So we have dr cap over d theta. So dr cap over d theta is theta cap times d theta over dt, so that's simply theta dot, plus we have dr over dt, so that's r dot theta dot plus r. So we have d theta dot over dt, so that will be theta double dot, whole multiplied to theta cap plus r theta dot. We have d theta over d, so that's negative r cap times theta dot. So let's write the expression in terms of r cap, the components of r cap and theta cap. So we have r cap, so from the first term we have r double dot, and in the last term we also have r cap, so the components will be negative r theta dot squared plus theta cap, so plus theta cap, so that will be simply, so we have r dot theta dot appearing twice, so that will be 2 times r dot theta dot, that's taken care of, plus we have r theta double dot, r theta double dot. So this is going to be the component of theta cap. So finally we have obtained the two components of acceleration vector. So like velocity vector, so acceleration is also going to have two components, so let's talk about them. So we have the radial acceleration, or the radial component of acceleration, so that will be simply ar is equals to r double dot minus r theta naught squared, and the angular component of the acceleration will be, angular acceleration is simply given by a theta, so that will be 2 r dot theta dot plus r theta double dot. So we are going to conclude today's lecture here. In the next lecture we're going to pick up the velocity vector and acceleration vector, and we'll try to understand in details about the radial part as well as the angular part for both the two vectors. So see you in the next tutorial. Thank you.